of part 2 of chapter 5. Last time we talked about the R and S configuration, how to determine if you have R or S, how to determine the priority. Today we are starting with like a physical difference in physical property of pair of enantiomers. So if you have two compounds that they are pair of enantiomers, let's say you have hydrogen, bromine, CH3, CH2OH, CH3, and then the mirror image as the HBr, CH2OH, and CH3. If you have these two compounds as pair of enantiomer, they are non-superimposable mirror images, so we know that they are pair of enantiomers. And if the structure on the left side is R, then the structure on the right side would be S. Just as a review, we determine the priority. So hydrogen would take the priority 4. And this is a Fisher projection. That means you have vertical and horizontal lines. If the low priority is on the horizontal line, that means it's coming toward you. And any group that are with vertical line is going away from you. So since hydrogen, which has lowest priority, is coming toward you, then if clockwise, the rotation going from high priority to low priority, if it's clockwise, then it's going to be opposite. So it's going to be clockwise would be S, counterclockwise would be R. So we have 4 for hydrogen, 1 for bromine. Then we have a CH3. If you can see here is the CH3. You have a CH2OH. So the first element is carbons. We cannot decide based on the carbon, but the second element attached to the carbon on top is oxygen. The one at the bottom is just hydrogen. So we have 1 and then 2 up here and 3 and 4. So going from 1 to 2 to 3, it's clockwise. And since it's clockwise, but hydrogen is on the horizontal line, the clockwise is going to be S. If clockwise, if the structure on the left side is S, the mirror image is going to have R configuration. You can decide that. That was the last slide we talked about it, or you can determine priority list for the molecule on the right side. You have 4 for hydrogen, 1 for bromine, 2 for CH2OH, and 3 for CH3. So going from high priority to low priority, or from priority 1 to 2, is counterclockwise, and counterclockwise is going to be R if low priority is on the horizontal line. So you have the low priority on the horizontal line, and the rotation of counterclockwise, meaning R, and clockwise would be S. So what's the point of difference? Like how these two compounds behave differently in real life? They have different functionality, especially like in human body, and in terms of the physical property, one would rotate the plane polarized light to the right side. The other one would rotate the plane polarized light to the, if one rotates the right side, the other one would rotate to the left side. So with that, we want to know what is a plane polarized light. A plane polarized light, because light, it travels in all directions. And if you put filter, only the lights that are aligned with the opening of this filter would pass through. So you have the light that is in traveling in single plane. So it's a plane polarized light. So you have the plane polarized light. What they do, they have the light source. Sometimes they use like a sodium lamp. And the light, when the light is generated, since it travels in all directions, they place a filter and then they get the plane polarized light. Now, if you have the plane polarized light, going through two filters. So if you have a filter and another filter here, so basically you have this space between the two filters. Now, if you place the sample in this space between the two filters, if your sample is a chiral compound, it's going to rotate this light to either clockwise or counterclockwise. It's going to rotate to the right side or it's going to rotate to the left side. If the light is rotated, and since these two filters are parallel to each other, the light will not pass through the second filter and it would be blocked. If the light is not rotated, it will pass through the second filter and you will see the light. Now, if the light has been rotated and it would be blocked, what can you do to see the light again is if the filter that you have, the second filter, if it's a mobile filter, if you can rotate it, you can move it, and you have to move it in a direction. So the design of the machine would tell you you have to rotate to the right side or to the left side. And you would rotate until you see the light again. Then you count and see how much did you rotate this filter in order to see the light again. That would be observed rotation of the observed rotation for this chiral compound. By how many degrees the light has been rotated. So you can measure that as observed rotation.
Professor?
Yes, let me see if I have a better picture to explain that. Yes.
The diagram on the left, when we were talking about the compounds, the one you just erased.
Okay.
The one on the left, even though the hydrogen was on the horizontal plane, and the horizontal plane is a wedge, correct? Because it's coming towards you.
Yes.
Right? So wouldn't that reverse it?
It would reverse it, yes.
Correct, but we didn't do that on the diagram.
But didn't I indicate that as a S?
Yeah, you did.
I did. So
Yeah,
if
but
I
it
indicated
should be R. It should be reversed, right?
No, it was
Okay.
clockwise, so it was S.
Because it's a clockwise and I said it's S, that's basically I reversed it. So I had
I see what you did. I see. Oh, okay, I see what you did. Okay, yeah.
So if it was going clockwise and I said this is S, that means that I had to reverse it basically.
I guess, yeah. I get it. All right, cool. Thank you.
That's okay. So if the light is when the light goes through the two filters, okay, when the light goes through in the sample, that is the sample holder that is placed between the two filters. If your sample is a chiral sample, is going to rotate this light. If the light has been rotated, then if you had the filter still in the original position, like this one parallel to the filter that you have up here, the light would have been blocked and you couldn't see it. But by rotating this filter to the same angle as the light that has been rotated already, then the light can pass through and you could see it. And this amount or this the angle can be measured as the alpha. So this basically, this diagram shows the light that has been rotated by sample. Now, if you have solvent like CH3OH, methanol, just a pure methanol in the sample holder, would that rotate the light? Would methanol rotate the light? What would be condition for a compound to rotate the light? It must be?
Must be chiral.
Chiral. Is methanol chiral?
No.
It's not chiral because your carbon is attached to at least 3 of the hydrogens. 3 groups are the same. So methanol is not chiral. Is water chiral?
No.
If you have water, would
Water
it rotate the light? is not chiral, is achiral, because if you draw like a plane of, there's a plane of symmetry, you can say it that way, or you could say two of the groups attached, they're identical, so it's not chiral compound. So if you have methanol or if you have water, is not going to rotate the light. But the compound that you're adding to methanol to dissolve in methanol is, if it's chiral, it will rotate this light. And the degree of rotation can be measured by rotation of the movable filter to align with the new direction of the light. So when the light comes in at the beginning is a straight up down, but you see as it's passing through the sample is being rotated. Is being actually rotated by the sample. And since that's been rotated, then you have to rotate the filter in order to align the opening of the filter to the light that has been rotated. And then you can find out by how many degrees has been rotated, and that is known as the observed rotation. So when we say observed rotation, it means like the higher the concentration you have in this sample, the greater the observed rotation is going to be. So observed rotation depends on concentration. It also depends on the length of the sample holder. If the sample holder length is expressed in decimeter, so you could have like a 1 decimeter, or you could have like 2 decimeter or 3 decimeter. So it depends on the length of this sample holder. So there are 2 factors that can change this observed rotation. Whenever you want to compare 2 compounds, you have to make it standard. So you cannot say 2 gram per 10 milliliter of this sample, or 2 gram per 8 milliliter of the sample compared to like 3 gram of the other sample in 10 milliliter. You cannot say that. You have to standardize it. So in order to standardize it, you change your observed rotation to a specific rotation. So when you have a specific rotation, that is like for a standard condition, that how much is the light is going to be rotated by that sample. One point, the plus or minus sign. If the sample is going to rotate the light to the right side or to the left side, it cannot be determined by looking at the structure of the molecule. By looking at the structure of molecule, you could say if this is S or is R, but you cannot say if it's plus or minus. If you take the plus for right rotation and minus for the left rotation, so you cannot say that by looking at the structure. This value or the sign of rotation, the direction for the rotation of the light, must be determined experimentally for each enantiomer. That's one point. Point 2, if you have pure sample of pair of enantiomer, that one is S, the other one is R. If S rotates the light by 5 degrees, a specific rotation for S is 5, for R is going to be minus a 5. If one is a plus 5, the other one is a minus 5. Condition, they both have to be pure sample, and they must be mirror image of each other. So if S is a pure sample, R is a pure sample, and these two are mirror image of each other, the specific rotation for these two is going to have exact same value and opposite sign. Okay, observed rotation would be opposite sign, but a specific rotation would be exact same value and opposite sign. The R and S, it doesn't mean, so this diagram basically shows that the formula that you have for 2 compounds, that they are both S, but one rotates the light to the right side, the other one rotates to the left side. So S and R doesn't mean that they are plus or minus, if they're going to rotate the light to the right side or to the left side, but experimentally, you can determine if the light is being rotated to the right or to the left side. Okay. So another diagram, again, based on the plane polarized light. when it's passing through the first filter is expected to be seen on the other end passing through the second filter as well. But since this light has been rotated, you have to, this is a movable, see, is a movable filter. It's been rotated, so you can see the light again coming out, and you are going to measure this value for alpha, or the degree of rotation of the filter, that you could see the light again, and is known as the observed rotation. The temperature usually is used because the temperature can, the higher temperature or lower temperature can change the degree of the rotation. For pair of enantiomers, opposite sign, exact same value, if with the condition that they are pair of enantiomer, meaning that they are mirror image of each other. The second condition, they must be pure sample. If it's a mixture of the two, is not going to be, is not expected, is not going to be exact same value and opposite. It could be the opposite, but still is not the same value. So if one rotates the light clockwise and the other one rotates the light counterclockwise, and if you have a mixture of two, what's going to happen? So if compound A is rotating the light clockwise and compound B, which is the mirror image of A, is rotating counterclockwise. If the component of the mixture, if it's exactly 50-50%, the net result of rotation is going to be 0 degree rotation. Because if one rotates by 5 degrees, the other to the right side, the other one will rotate by 5 degrees to the left side, the net result is going to be 0. Now, if the percent composition is not 50-50, let's say if you have 75% and then 25%, what's going to happen? If the 75% is for plus and the 25% of the minus, if you mix it together, what's going to happen? This is going to rotate the light by 75, and then this would bring it back by 25% of it. It would be back, it would be canceled. So it came like 75, but it was rotated back by 25. The net result is going to be 50. So if you have a mixture of 75 plus and 25 minus, the net result is going to be 50 plus. This 50 plus is basically the overall rotation and is also known as enantiomeric excess or percent purity. So enantiomeric excess, that means that you have 50% more of the plus compared to the minus one, enantiomeric excess. So you get 50% of it if you have this combination. Now, if you have a 60-40, that would be different. For 60-40, the overall is going to be, what would be the overall?
Plus 20%.
20%. So you would get 20% rotation. That would be the observed, and that is the enantiomeric excess, or EE, enantiomeric excess.
So the numerical values won't always be the same, correct?
No.
Okay.
No. So if you have a mixture of enantiomer containing R and S, then the term of enantiomeric excess is going to be defined, the observed rotation over the specific rotation of a pure enantiomer. The specific rotation of a pure enantiomer is given in the books. So the observed rotation is what you are measuring in the lab. If you have the specific rotation for pure sample, we divide the observed by the pure sample times 100. That would also give you enantiomeric excess. and it's basically the same value. Those are hypothetical example. If you have 75-25, it's going to add up to 50, and is a percent mixture if you have the percent composition of it. So what does enantiomeric excess of 40% means? Means that you're like, if this is for plus, that means you have 40% more of the plus compared to the minus. So 40% more of the plus. So if you have like a 70-30, that means that you have 70% of the plus one compared to the other one. So you have more. So this is one formula that you can calculate the enantiomeric excess, observed rotation over the specific rotation of the pure sample times 100. That would give you the
Professor, are they going to let us know which one is the pure sample, since we're comparing two different compounds?
Okay, if the specific rotation is given to you, that means it's for pure compound. Okay, for example, in the example that you have here, a specific rotation of S2-iodobutane is 15.9. Determine the percent composition of the mixture of R and S if the specific rotation of the mixture is 3.18. Which one is extra in this example? The R is in excess amount or the S is in excess amount?
S, right?
I already gave you the answer, sorry. Okay, the minus one. So if S has a specific rotation of a plus sign, the R is going to be extra because the overall observed rotation is negative. Does it make sense?
Yes.
So you are getting only.
Can you please repeat it? I'm sorry, I didn't get it.
Sure. If the value for the for one of the enantiomer, if the specific rotation for pure sample is given, and that is plus, okay? So we know that S is going to be plus and R is going to be minus. When you have a mixture of R and S and overall is minus, which one is in excess? R or S would be in excess amount?
R.
R would be in excess amount. So the excess compound, the excess enantiomer would be in the R value with the excess amount. So the excess enantiomer, the sign is from the enantiomer in excess is level. That means left rotation or minus sign. And since we already know that S is positive, then we can say R is negative. The R value, the value of R or percent of R is going to be higher in this case. So we are going to calculate the optical purity. To calculate optical purity, you are going to divide the observed rotation over a specific standard rotation times 100. So 3.18 divided by 15.9 times 100, that's 20%. What does it mean, 20%? Based on this information that you have. This is a mixture of R plus S. Percent R plus percent S.
So it's going to be 60-40.
So this means that there is 20, so the meaning of it is there is 20% more R than S. Does it make sense?
Yeah, because 20% would be the difference between the two, correct?
Yes, 20% is the difference between the two, is the optical purity. Excess of the enantiomeric excess, that means that one is this much, this percentage greater than the other. So it means 20% higher than the S. And how do we know that R is in excess amount? I'm just repeating what I said before, because overall it's showing a negative sign. So if overall shows a negative sign, that means you had more R than S. So 20% more R than S. Numerical value of how much is going to be more can be calculated by the numbers given. So a standard is given, a specific rotation, and this is the observed one for the mixture.
That's the same formula as the enantiomeric excess?
Yes, optical purity and enantiomeric excess is the same thing.
Okay.
Yes.
So even if the number is bigger for the plus, you're still gonna look at the negative?
Okay, the
No,
number that is given
negative is
for
the
the
total.
plus one, that's for pure sample. That is just a piece of information that you need to know to have for a standard. So what is the specific rotation for pure sample? That's a standard. If you had 100% S, a specific rotation is going to be 15.9. If you had 100% R, what would be the value?
Negative 15.9.
Negative 15.9. Now, if you had 75% R and 25% S, would the rotation for the mixture be negative or positive? If you had 75% R, I'm just putting the hypothetical number here, 75% R and 25% S, would the value be negative or positive? The rotation, the specific rotation for the mixture.
It'll be positive, right?
No,
Which one is negative? R negative or S negative?
R.
We know S is positive, right? If we have more R than S, then this sign is going to be negative because you have more R than S. If you had 75% S and 25% R, what would be the sign?
Be
Plus,
positive.
it would be positive, right?
Yeah,
Because you have more S than R. If you have more S than R, then and since we know S is positive, then the overall sign is going to be positive.
this only works if you have the same compound, right?
Yes, it has to be same compound. The R and S, the enantiomeric excess, it only applies for the pair of enantiomers that they are mirror image and non-superimposable. Yes.
Gotcha.
So this, if we don't have this percentage values, but we do have the specific rotation, we can find the enantiomeric excess or optical purity. And if we look at this number, what does that number means? For 20% means, it means that we have 20% more R than S. Okay, so.
Well, it depends on what the specific rotation is, right? Whether if it's positive or negative.
Yes, because the specific rotation was negative and we know that R was negative, so that means the excess amount is going to be an R.
Negative 20%. Yeah.
Yeah. So it's going to be 20% more R than S. So you can do a mental math and you come up with like 60% R and 40% S, or you can set up an equation. If you set up an equation, how would you set up your equation in order to find those combination? Now you would say S plus R is going to be 100, right? Because you have only two compounds. So S plus R is 100. And then R minus S is going to be 20, right? Because we have 20% more R than S. We have 20% more R. If you write it, it makes sense. More R than S. So what does it mean? It means R minus S is 20. Or percent R minus the percent S is 20%. Percent S times plus percent R is 100%. And now you have equation and you can solve it. If you add these two, if you add, the S would cancel with the plus and minus, then you have 2R equals 120. You divide both sides by 2, and that would be 60%. And if R is 60%, as a result, S is going to be 100 minus 60, and that is 40%. So first you find this enantiomeric excess, then you would set up equation, and you find the value for each one. Okay. So 2L, or basically in this case, I wanted to make sure that you understand this is a 2R, is 120, and 1R is 60. So S is going to be 40%. Okay. Any questions about this before I move? No questions? So one more time, for a compound to be chiral or to rotate plane polarized light, it must be chiral. In order to be chiral, it must have chiral center, and that happens like of 90% of the time. Your compound that is chiral contains a chiral center 90% of the time. Now if one rotates the light to the right side, the other enantiomer will rotate to the light to the left side. If it rotates to the light to the left side, by convention we say negative, and this would be positive. Also, the positive one is also designation of a D, can take the designation of D, and the negative one L. So this is like a levo and dextro. So it's the left rotator, right rotator. These by convention, D and L also is used in exchange of a plus and minus. If you see a label that it says plus minus, or you see that it says DL, that means is a mixture of both enantiomers, is not purified. If it's a chiral compound and it is pure, it would say either just R or just S. There are some compounds that they do not have chiral center, but they are chiral, and that would be for compounds that they are like non-mobile conformers. Rotation around this carbon-carbon single bond is not free because of the steric hindrance. So it cannot, without breaking the bond, you cannot rotate it. And if you take this compound, try to superimpose for this compound, they are non-superimposable. They are mirror image of each other. So they can be classified as a pair of enantiomer, even though you don't have chiral center. Another case, and these are not very common, okay? They are not very common. And I said like 90% of the time you have chiral center and you have chiral compound. Another exceptions that you have like allenes. Allenes are the molecules that they have 2 consecutive double bonds. So you have CC double bond, CC double bond. And if you have allenes, 2 groups, 2 different group attached to the carbon and to both ends of the allene functional group. If these 2 groups are different, then you could have, because the rotation around carbon-carbon double bond or consecutive or allene is not free, then and if they are not mirror image of each other, you do have the pair of enantiomer. So the compounds are chiral. Just keep that in mind in case if you get a question like what are exceptions to the chiral compound. Otherwise, chiral center, chiral compound. And their explanation is here. They are chiral even though they have no chiral carbon. Because you have a carbon here with the sp hybridization. For Fisher projection, we have been talking about Fisher projection already. Know that we have the vertical line and the horizontal line. Horizontal line is coming toward you, and then the vertical line, the groups are going away from you. And if the group with the lowest priority is on the horizontal line, clockwise would be S and counterclockwise would be R. When we talk about the pair of enantiomers or how many possible structure you could have for a compound, if you have one chiral center, that's like 2 to the power of n. If n would be number of chiral center, if you have your compound has only one chiral center, that means that you have only one pair of enantiomer or only 2 chiral compound as a result. But if n equals 2, that means your compound has 2 chiral center. There are 2 to the power of 2, and that is 4 possible. And it doesn't mean that it's going to be 4 different compounds, but there are 4 possible structure that they could be mirror image or not mirror image, but they still are a stereoisomer or geometrical isomer of each other.
Professor, what does that N means again? I'm
N
sorry.
is number of chiral center.
Oh,
I kind of, let me, maybe on the next slide we have that. No, not yet, but we will get to that. N is number of chiral center. So if your compound has only one chiral center, expect 2 enantiomer, one pair of enantiomer or 2 enantiomers. If your compound has 2 chiral center, then the possibility of arrangement, it's greater around the chiral center. You get more than 2 compounds for that. And I do have example of that. I will show you. So determining R and S. Now the hydrogen, which is the group with the low priority, is a vertical. So clockwise is R. This is just emphasis on it. We have seen this before. The group with the lowest priority is on the horizontal line. Clockwise is going to be S. So you have to switch it around. You have group with a compound with 2 chiral center. So for this compound, the value for N is 2. We have a chiral center and another chiral center. If we have compound with 2 chiral center, there are 2 to the power of 2. In general is 2 to the power of n, and here is 2 to the power of 2, and that is 4 possible structure for this compound. So we have these 2 possible structure. If you have CH3 and CH3 are, on the carbon chain is on the vertical line. So carbon 2, you have hydrogen and OH, and carbon 3, you have hydrogen and Cl. So if the OH and Cl both are on the right side of the molecule, the mirror image of that, it shows both of them on the left side. These 2 are mirror image of each other. These 2 are pair of enantiomers with respect to each other because they are mirror image and they are non-superimposable. You could have another case that OH is on the right side, but Cl is on the left side. If you look at the mirror image for this compound, you draw this dashed line here, and that shows the 2 mirror images that you have for the molecule. OH is on the right side, Cl on the left side, and vice versa. For the mirror image is going to be different. Now, we learn about some definitions. Compound 1 and 2, with respect to each other, these 2 are a pair of enantiomers. So 1 and 2 are enantiomers. What about 3 and 4? 3 and 4, they are enantiomers, right? 1 and 2, they are enantiomers. What about 2 and 3? It's 2 and 3 enantiomer or not? question mark enantiomer?
No,
They are not enantiomer. Why they are not enantiomer?
because
They are
they're
not-
not mirror images of each
Okay,
other.
because they are not mirror image of each other, they are not enantiomer. Are they isomers? They are geometrical isomers or not? They are geometrical isomers, right? Because they are geometrical isomers and they are not enantiomers. So the answer to that question was no, these are not enantiomers. If they are not enantiomers, they are classified as diastermers. Diastermers, those are the geometrical isomers of a compound that they are not mirror image of each other. So 1 and 3, they are diastermers. 2 and 3 are diastermers. 2 and 4 are diastermers. So we have diastermers, diastermers, and diastermers. 1 and 2 are enantiomers, and 3 and 4 are enantiomers.
Diasomers are the same, and then enantiomers are the different, correct?
Enantiomers are mirror image of each other,
Your image, yes.
but diastermers, they are not mirror image of each other.
But they're isomers?
They are isomers, yes.
Okay.
The molecular formula is the same. So basically, compound 2 and compound 3, or structure 2 and 3, which I'm going to circle, 2 and 3, they are still coming from the same molecular formula, the condensed formula that we have up here for 3-chloro-2-butane, sorry. So we could have enantiomers or we could have diastermers. And we got 4 different possible structures because we have 2, n equals 2, or we have 2 chiral center for this molecule. So this is just explaining what we already talked, that 1, 4, and 2, 3, and 2, 4, these are diastermers. They are not enantiomers. You had 2 pairs of enantiomers, and diastermers are non-mirror images. They are non-mirror images. For cyclic compounds, we do have cis or trans isomers also. So if the 2 groups are on the same side of the ring, is going to be cis, and if they are in opposite side, is going to be trans. And if you have symmetrical, like if you have asymmetry or a chiral carbon, then you could talk about the mirror image, and you could talk about the enantiomers. But if there is no chiral center in a cyclic system, and you don't have enantiomer, it doesn't apply. Enantiomerism does not apply. If you have a cyclic system that is, especially if it's cis, and the 2 groups are the same, so basically a structure like this, you have a CH3 and you have CH3 coming down here, CH3. This compound it has plane of symmetry. So you can, if you cut the molecule in half, it's basically has internal mirror image of symmetry, or there's a symmetry, or these are internal mirror images. A compound like this is called meso compound, MESO, meso compound. That means this compound is going to be achiral. If you have 2 chiral center, so these are 2 chiral center. So if you have a compound with 2 chiral, more than 1 chiral center, but there is a plane of symmetry, then you have meso compound. There's a definition, new definition for it. The compound is meso. If you have 2 pair of enantiomers, if you have like a pair of enantiomers, and you get a 50-50 mixture of it. 50-50 mixture of pair of enantiomer is called racemic mixture. So these are some of the definitions that you see in this chapter also. So you have pair of enantiomer, you have diastereomers, you have meso compound. Meso compound would be the one that you have internal mirror of image or plane of symmetry. And if it's a mixture of 50-50 mixture, exactly 50-50 mixture, that means your compound, there would be the net result or the net rotation is going to be 0, right? If one rotates by 10 degrees to the right, the other one would rotate 10 degrees to the left, the net result would be 0. If the net result of rotation of plane polarized light is 0, then the compound is going to be considered as achiral. If you have a meso compound, because of the plane of symmetry, is going to be achiral. But if you have a compound that you have the compound and its mirror image and they are not superimposable, you have pair of enantiomers, each one of them is going to be chiral compound. Okay, I'm looking for another structure that shows the plane of symmetry. Okay, this structure, it shows plane of symmetry. You have two chiral center. And if you have two chiral center, then if both bromides are on the same side, if two bromides are on the same side, then it's going to be, it's going to have internal mirror image, then you don't have the enantiomer of that compound. So this compound has plane of symmetry, so there would be no fourth compound. So total is going to be 3 in this case. Let me count it. Or draw the Fisher projection. So it would be a practice for you, and also, you understand why we have 3 compounds versus 4 compounds. We have 2 chiral center here. Going to draw the CH3 and CH3. The first one, I'm going to do both BR on the same side, and I try to draw the mirror image of this. When I try to draw the mirror image of this compound, it's going to look like this. Okay. These 2 compounds, if I just take this compound and shift it over, is not going to superimpose, but 180-degree rotation is allowed. So if I rotate by 180 degrees and I shift it over, the bromines are going to cover each other. Then you do have a, they're going to be superimposing. So that means you don't have 2 compounds, it's 1. Before testing even or rotating for 180 degrees, you could just draw this line here and say, if I draw a line through this molecule, it's going to cut the molecule in 2 exact same half. So this is a meso compound, and if you have a meso compound, there is no mirror image for meso compound. Another word, if you have a meso compound, the compound and its mirror image are same compound. Okay, so these 2 are equal, the same compound. So I have 1, 2, and I said that I'm going to draw all 4 of them. So we have Br in one side, hydrogen, and then Br and hydrogen. You have a mirror image for this one, Br, hydrogen, and hydrogen, Br. So structure 1, structure 2, structure 3, and structure 4. What is the relationship between structure 1 and 2? What's the relationship?
They are enantiomers.
Enantiomers.
I'm going to say they are the same.
They're a mirror image, correct?
I would say they are the same. Because what is specific about structure 1, I'm talking about the one that I labeled 1 here. Okay, these are 3 and 4 are pair of enantiomers, but 1 and 2, because of this plane of symmetry, this compound is called meso. A meso compound is same, you see this equal sign here, is the same as its mirror image. So they are not mirror image of each other, is the same compound. So if you look at the relationship between 1 and 2, it's called same compound.
That's because
Can it
they're
be
symmetrical, right? Like you cut them in
Yes.
half and they're the same. Okay.
Yes. What about 3 and 4?
Those ones are enantiomers.
These are enantiomers. Yes, these are enantiomers.
They're
So,
enantiomers because
They're mirror images.
they are mirror image, and there is no plane of symmetry. If I cut this molecule in half through here, and I try to fold it, is Br and hydrogen, they don't cover each other. And if I draw a line vertically, it's not going to cover either. Okay. So what about 1 and 3? How would you classify 1 and 3? Relationship between 1 and 3. It's 1 and 3 same compound. They are different compound. Are they pair of enantiomer, or they are diasomers, or they are racemic mixture? What they are? What are they?
Diastomers.
Diasters.
Very good. So we have pair of diasomers if they are not mirror image of each other. We have pair of enantiomer if they are mirror image of each other and they are non-superimposable. If they are mirror image of each other and they are superimposable, is the same compound. That's the case here for the meso compound. So we have 4 possible structure, but since 1 and 2 are the same, we end up with only 3 structure for this molecule with 2 chiral center. So when we say 2 to the power of 2, that is 4. This is the maximum, or 4 possible structure. But since 2 of them are the same, we end up with 3 structure assigned to this molecule.
Professor, doesn't the skeletal formula show that both bromines are on the same side though?
Yes,
So then how
and
would
it's
you have
the same thing as structure 1. So this is coming from structure 1.
yeah.
Both bromines are on the same side, so we didn't draw another one, both bromine on the same side.
it's the
But
same molecule.
that wouldn't be for 3 and 4 though, right?
No, 3 and 4 is like this. 1 is 3. My 3 is 1 from the slide, and then 3 for this one, and these 2 are the same compound. The cis one, the 2 bromine on the same side, is coming from this.
Number 1 is number 3.
Either 3 or 4. Let's see.
But doesn't the horizontal line indicate that the bromine's coming to you? There's 2 bromines, one's going away.
One is going, yes, one is going to one is on the right side, one is on the left side. So when we are drawing the Fisher projection, it's not exact copy of what we have here, because we have to decide either we are drawing the carbon skeleton on the horizontal line, or we draw for Fisher projection specifically, carbon skeleton must be on the vertical line. So we cannot have carbon and then carbon on the horizontal and vertical line. Or the carbon skeleton must be on the vertical line. So if you draw the carbon skeleton, then you have to see like hydrogen on one side, bromine on the other side. For the next carbon, bromine is on the whatever side takes this bromine, the other side would take the bromine. And that's what kind of represented here. Okay, for carbon 2, bromine is on the right side. For carbon 3, bromine is on the left side. That's what is showing here.
So you're looking at it from like a head-on perspective.
Yes, because the carbon chain must be on the vertical.
On the vertical. Okay.
I'm sorry, Professor. I'm still a little confused as to why 1 and 2 are the same and not just enantiomers.
Okay.
Because they look mirror images, but how are they?
They do look, but there is a plane of symmetry here. If there is an internal plane of symmetry, is a new definition, and that compound is called a meso compound. Okay, so MESO. So you have a meso compound here, and the rule is meso compound and its mirror image are the same compound. These two are not different compounds. That only happens when you have a meso compound. It only happens if you do have this plane of symmetry here.
Does the plane of symmetry then always have to be within the molecule, like in the middle,
Within
like
the
that?
molecule, yes, only within the molecule, yes.
Okay. Thank you.
You're welcome. It's like a specific case that you have internal mirror image. That means you draw a line, it cuts the molecule to two same half.
And that's called meso.
Yes.
Okay.
Are these two superimposable? It's explaining the same thing over. And these two compounds are superimposable. It may not be easy to see it, but you could actually rotate this by 180. So this would come over this hydrogen. I'm sorry, CH3. This CH3 would go here. If that happens, these bromines are going to be in this area and the hydrogen would be on that side. 180 AD is allowed rotation. So you basically flip the molecule by 180. Or the way that I said it, it doesn't need imagination really. It needs the definition if it does meet the definition. But the way I said it, if your molecule has internal plane of symmetry, that means your compound now has a new name and it's called meso. And if it's a meso, the compound and mirror image of that is identical, or they are superimposable mirror image. And they are the same. Okay, so meso or meso compound. So you have plane of symmetry. You see that the molecule is cut in exact same half, or in this case, both of in the 3D structure, both bromines are going to same side and is known as the meso compound. There are other examples of the meso compound that if you cut the molecule through vertically like this, you would get both like cut in exact two same half. So this is also a meso. And if you have a meso compound is asymmetric or achiral. Okay. So it's repeating of the same. This is another example. You have a diol here because of the plane of symmetry that you have here. This is a meso compound. But if OH is on one OH is on either side, then you do have pair of enantiomers. Is another example. If your molecule has plane of symmetry, like a cyclic compound, it's called meso compound. So if it's meso, you don't have pair of enantiomer. Do not draw the mirror image for compound that is meso. And how do you know it's meso? Try to find the plane of symmetry. See if the molecule cuts in exact same half, like two same half. Okay. So how would you recognize you have pair of enantiomer or you have a diastereomer, pair of diastereomers? First of all, the molecule, the two molecules that you are looking at, they must have same connectivity. If they don't have same connectivity, then you have structural isomers or constitutional isomer. You learn about those in chapter 3. If they have same connectivity, then with the same connectivity, then the next question comes up: are they mirror image of each other or they are not mirror image of each other? If they are mirror image of each other, it would be enantiomer. If they have same connectivity, but they are not mirror image of each other, it would be pair of diastereomers. Now, do you see plane of symmetry or you don't see plane of symmetry, like internal symmetry? If yes, it would be meso compound. If no, it would be diastereomers. So these are some of the examples, like let's say structure is given to you, and then you're asked, are these enantiomer, same, meso, diastereomer? And you should be able to recognize it based on these. Okay, you have the solution here. The question in the previous slide, and then your solution, please look at it. You do have the compounds. You have the slides. It's just how much time we have. We do have time for your quiz, so I could continue on this. So you want to first find your, like, how would you determine? Is that more of a practice, determining S and R? If you determine S and R for a compound, just something else that you want to know. Let's say you have carbon 2 and carbon 3, both of them are chiral. So let's say if you have 2R and 3S, that's one compound. And then you have compound 2. These are hypothetical. Compound 2 is a 2S and 3R. Compound 3 is 2R and 3S. Then you want to find the relationship between these two. What's the relationship between, out of ones that I wrote, if I determine the configuration for each one, each carbon of different compound already, and I come up with this set. So what's the relationship between 1 and 2? In this example, 1 and 2, are those same compounds? They are pair of enantiomers or they are diastereomers?
Those are enantiomers.
The rest of the molecule is going to be the same, okay? These two, 1 and 2, is going to be enantiomers. And how do you know is enantiomer?
Because they're opposite. So you have 2R on one, so you have 2S on the other, and likewise with 3.
So you have 2R changing to 2S, and the 3S is changing to 3R. Because it's opposite configuration in the same location, it's going to be pair of enantiomers. Enantiomer. What about 1 and 3?
Same.
1 and 3, you have 2R and 3S. So 1 and 3 is going to be the same. Very good. Okay. What about 2 and 3?
Enantiomers.
Also enantiomer? Yes, because 2 and 3 are this. If 2 and 3 are the same, then it's going to be both of them enantiomer to 1. And if I have compound 4, that is 2S and 3S. What would be the 2 and 4? Relationship between 2 and 4?
It's different.
Are they pair of enantiomer? The choices are they enantiomer, same, or diastereomers?
I guess I would make them diastereomers.
because they are not the same and they are not enantiomers. So it must be diastereomers. So we have diastereomers. Okay. So if the configuration changes completely, it would be opposite in every location. Is going to be pair of enantiomer. If one changes, but the other one doesn't change, then it's going to be diastereomers. If all change, it would be enantiomer. If one change, if one doesn't change, it would be diastereomers. If none change, it's going to be same compound. Okay, let's see if these two compounds, they are same or they are pair of enantiomer or they are pair of diastereomers. We already have determined as a practice. What's the priority? Which one takes the highest priority? I know the hydrogen would be lowest priority. Which one is high priority? OH or this one? The group below.
OH.
OH. OH. We look at one atom at the time, not as
Oh, okay.
we just take one step at a time. So that's one. This is going to be two, obviously, because this carbon is attached to bromine, but this carbon is only attached to hydrogen. So that is 3. So if we are going from 1 to 2 to 3, and it is clockwise, for this carbon is clockwise, hydrogen is on the vertical line. What does clockwise means?
Hydrogen on the horizontal line, right?
Yes, sorry, on the horizontal line. I'm
Then
sorry.
that's S configuration.
That is going to be S configuration. So we have S configuration here. And this one is, it already says is R. So we have a 2S and 3R. Okay, 3R. We're just going to take and believe it. And this one is 1, 2. Okay, is the same thing. And 2 here is going to be 1, 2, and 3. So counterclockwise, hydrogen is on the horizontal line. 3 is going to be R. So is a 2S and 3R. We have 2S, 3R. We have 2S, 3R. These two compounds are the same. And obviously they are a copy of each
Oh,
other.
we have 3S on the bottom.
3S?
Believe so, yeah.
No, I think it's 3R. Because it's counterclockwise. And hydrogen is coming toward, is on the horizontal line. So it would be, it's going from bromine to the top group, and then it comes down. So it's like this rotation, counterclockwise.
Oh, okay.
It's going to be R, yes. It's exact same copy. I mean, this was just trying to make not too crowded, the top and the bottom. The top one is showing the configuration for 3R, and the bottom is showing for the 2S, but we practiced the other two. Is how would you determine? Okay, so you have to pay attention if the lowest priority is on the horizontal or vertical line in order to say if the clockwise is R or if clockwise is S. We already did this practice before, but if you have like a 2R and 3S versus 2R and 3R, these two compound A and compound B, what are relationship? What's the relation between compound A and compound B?
Diastomers.
Diastomers.
Diastereomers.
Very good. Okay. What is the relationship between compound B and compound C? Compound B and compound C. B and C.
Enantiomer.
They are enantiomer because we have 2R, 3R. Here we have 2S, 3S. Very good. Okay. So we have pair of enantiomer, and then we have, what is the other name for this compound? How would you classify this compound?
Meso.
A compound is meso because you have internal mirror of image of symmetry or plane of symmetry. You have internal mirror image or plane of symmetry. You have it cuts the molecule to same half. Obviously, we are not going to have an enantiomer for this one. Okay. Compound A and B are diastereomers. A and C are diastereomers. B and C are enantiomers.
How come the one above that is meso?
This is the same compound, actually. We're just bringing down and drawing the 3D structure as the what is it? Fisher projection. It's the same compound.
But the direction of the HO, just because they're opposite, makes them symmetrical?
Because you could rotate it, maybe?
It's like it's a trans compound.
Yeah.
Yeah, the groups that are attached to it. See, these groups that are attached to it, they're all the same, and they are kind of in this case, just look for center for symmetric. Let's say if I start from this OH, bring to the center and continue, it reaches to another OH, and then COH, you go to the center, and then you go to the other group, it reaches to the other group with the same distance.
I
So
guess the wedge and the dashed bonds are throwing me off.
Yeah, me too.
you would look at this as the center for symmetry. Yes, you're right. That is
So whether if it's a wedge or a dashed line, it doesn't matter in symmetry. It just matters that they're on like mirror images.
yeah, if you say that is going to be, so first it's not easy to determine in that structure. You have to take it to the to this eclipse form and then determine it.
Okay.
So
Okay, yeah, I see now.
okay, just as the emphasis, if you have opposite configuration, pair of enantiomers, so you have the pair of enantiomers here, the specific rotation would be opposite. Okay? Everything else is the same. Like the solubility for these compounds are the same. Melting point is the same. But the only difference between pair of enantiomer is that one would rotate the light to the right side, the other one to the left side. And that's the only physical property that pair of enantiomers they have in point of a difference. Rotation of plane polarized light are not the same. If one is to the right side, the other one would be to the left side. And for the diastereomers, they have different physical property. So in order to change pair of enantiomers, to separate pair of enantiomers, I don't know how many of you have lab. Your experiment 7 at Central Campus is resolution or separation of pair of enantiomers. First, you have to change them to pair of diastereomers, and then you can separate them, because pair of diastereomers, they have different physical properties. Pair of enantiomers, they have same physical properties. You cannot separate pair of enantiomers by physical means. First, you have to change to pair of diastereomers. The technique is called resolution. So basically, you have to resolve it. Okay, good. Just okay. You ready to take the quiz? I have to grade your papers for next Tuesday, so let me do what I can do here.
Can we go over quickly, how to tell